So my name's Dave. I graduated right about 10 years ago, and it's very funny because I actually gave, like, maybe in a couple months, it'll be 10 years since I gave my capstone presentation in this room. Very, very odd. I couldn't possibly decline the opportunity to talk. So I think there are three main things that, when I was in, hopefully, your guys' shoes, that I kind of would want somebody to say. I won't call it advice, because I don't particularly think I'm old enough or wise enough to call it advice. But what are the three things that maybe I would have liked somebody to tell me? And so I think what I've come to in general is it's really important to keep your focus on the end goal and not get lost in the individual moment or the key problem set that you're focusing on right now. It's really important to take a much larger view. The second piece is you are surrounded by innovation. I will refuse to let anybody out of this room think that they are innovation or creativity limited. It's a really important piece. And then the third thing is, what are the key pieces moving forward, and what should maybe the next generation be focusing on to try and build the correct tool sets to be really, really good contributors to the workplace and make yourself look as good as you possibly can to potential future employers. So when it comes to focusing on the end goal, it's very easy to lose sight of the bigger, broader, programmatic or project picture. At Boston Engineering, where I work, we have this phase gate process. And it's all about starting early on with requirements, moving through basic engineering development, moving then through to detailed design, all the way through a potential future phase of continuing engineering support and hopeful long-term revenue for the company. At its most basic point, there's kind of a ideate, engineer, advanced phase gate process. It's important to note. At the most basic layer, it all starts with innovation. There's a really great book out there by a guy named Donald Stokes. It's like $12 on Amazon, but I'll save you the $12. Wikipedia has a pretty good write-up on it too, if you don't believe me. And it's all about how do you bound the fundamental understanding and how do you bound technological innovation. He describes it in two axes. The first axis is, are we really trying to understand the core of the problem? Are we looking deep down into what is the problem that we're really trying to solve? So that's one axis. And the next axis is, how soon can we realize that goal? Is it something that we're just trying to understand for the sake of understanding, or is it something that's really practical? So there are a couple pretty good examples of where you might end up in this matrix. The bottom left, if you're not thinking about use or you're not thinking about fundamental understanding, we'll call that we'll call it the Uber or the Lyft quadrant. You should probably get a job with Uber and spend some time figuring out what you really want to do. Moving outside of that corner, if we look maybe at the top left, so somebody that's really interested in fundamental understanding but not really focused on what the near-term application is, that's Niels Bohr. Very, very, very active, very fundamental physicist. We probably all heard about him at some point during, physics or chemistry 1. Really impressive in understanding how the fundamentals of an atom are broken down and work together. He admitted that he didn't really know why. He just knew this was something that was really important. Now, I'm not suggesting that that's a bad thing, but I think it's important to realize that there is a very small group of people that are enabled to do that on a day-to-day basis. You have to be incredibly smart, you have to be incredibly driven, you have to really know exactly what you're going for to be able to pursue a career in furthering knowledge without any product on the backside. In the bottom right, where there's no real interest in the fundamental understanding, but you're really focused on how it's used, that's Edison. The perfect example is Edison. I have rows of filaments, I have columns of gases, and I have cheap labor, and I will just make them test all of it. And to his credit, you could say he revolutionized the way we see things in our, the light in our everyday environment. However, that wasn't really a higher order focus, or really higher order look into trying to understand how everything works. If you look at the top right, that's Louis Pasteur. It's kind of the fundamental of the book. Very impressive chemist. He said, I really need to understand viruses and bacteria, because the second I understand viruses and bacteria, I can get to vaccines. And my goal is vaccines. I want to help the nation. I want to help the world. but I need to get some really good fundamental understanding to get there. So if we model when we're thinking about early stage innovation and really kind of bottom basement science, if we focus much more further in the top right corner, I think in general, it's a much more productive space for us to be in, and it's much more helpful for the companies that we might work for in the future. After base innovation, you have to think of the actual engineering. So anybody anybody tell me what this is? What's up?
It's something Narrows Bridge?
Tacoma Narrows, right. Yeah, and I'd hate to be on the design team that worked on that. I mean, it's every textbook, absolutely every textbook you ever see has a detailed story about this. And I think the big lesson is you got to take into account the wind when you're designing a big bridge. That was the gist. The wind came through in this valley. It matched the harmonic of the actual structure, and all of a sudden you see these, horrific things. It could have been an absolute disaster. The dangerous thing and the pitfall to think about when we learn these lessons is to think, well, the lesson that we should have learned is think about the harmonics and think about wind. That's not really the takeaway. I was in London a couple weeks ago, and there's a big building. I thought it was kind of fascinating. It has this really big garden sitting on the top. It's really interesting. It's kind of a little bit of a figure point inside of the city. But what's funny about it is that curve at the right time of year can actually focus the sun, and you can actually cook on the sidewalk where that focuses all the light, right? So we study these textbook examples of how not to design things, but we're not really taking the lesson that says, what are the questions that they didn't ask? Obviously the question that they didn't ask is, what is the wind like? What are the harmonics like? But the lesson is not study wind and study harmonics. The lesson is always keep an eye out for what the critical risks are and try and attack them ahead of time. That's the big picture, and I think it's something that gets lost, at least for me. I remember it getting lost a little bit in basic engineering curriculum. When you step up from even further up from just R&D and you get to the product level, there's a lot of problems in that space as well. So I got a couple examples. I don't trust my hairline to tell you, but I've never seen a Betamax. This is what fought with VHS. So it went Betamax, VHS, and then CDs, DVDs, Netflix, and Snapchat. So we got to move way back, right, all the way back. So this is Betamax. Technically, most everybody would say it's a superior product. However, they kept their, not codecs, but the codecs of the day, they kept that proprietary. So it really wasn't adopted. So VHS came out and was the big winner in that market segment. It has nothing to do with the technology base. It's somebody that misjudged the market. Again, we can talk about amazing successes that come out of Apple, but they have a handful of black eyes as well. So this is the Newton. It was the PDA before PDAs. Incredibly advanced. It was actually one of the first systems that would recognize your hand gestures. It's really impressive, and it's really, really novel. The problem was they really misjudged the market. Nobody really wanted to use their hand gestures. Nobody really wanted to write on that pad. So it was a big flop. We all know they kind of flipped the switch on that and were able to come out with an iPod that was incredibly successful. Just because, though, they came out with an iPod, that doesn't mean some other company can come in and do the same. So there's the Zune. I don't know if anybody remembers a Zune. Talk about interesting feature sets. The coolest part about that was you could share a song. They had all these ads about, you're on a train and a cute girl goes by, you can share a song, they get to listen to it for 2 days or something. It was really interesting, really fascinating way to try and share music in a way a little bit before music sharing, or in a point in time when music sharing wasn't really a good thing. But then again, look at it. You have to insert the CD into your PC, and then it's like, we can just immediately look at that and be like, I'm just going to buy an iPod. Why would I even mess with that? So even if the market's there, the industry is there, you have a good technical product, that still doesn't mean you can actually get all the way to the end. So these are really kind of basic thoughts, but they're really challenging to execute, especially in the framework of a company that I work at, which does really basic engineering all the way through product development, and then really trying to build on product development work to try and actually build large quantities, hundreds of millions of products. Summarizing here, some of the perceived and latent needs, those are really critical. The obvious needs are important, but the needs that aren't so obvious, when a customer doesn't tell you what their need is, that's what we call a latent need. It's really important to understand that and be aware of it so that you can try and point to it. So you can really try and find those pain points and execute on them. On the engineering side, you need defined and testable requirements. If you can't test to prove that your system is working better than your competitor, then it's just BS, and you run a massive risk of disappointing everybody when the product actually launches. And then optimistic and pessimistic business cases. My guess is Microsoft didn't really think about the pessimistic side of the Zune, and it was a big problem for them financially in the market and otherwise. So next point of view here is don't let yourself be limited by inspiration. It's absolutely everywhere around you. At Boston Engineering, we do a lot of work with biomimicry. So let me give you a brief introduction into biomimicry kind of en masse. The theory behind biomimicry is all about leveraging something that's occurring in nature, something that's evolved or something that's working well, and trying to apply it to a new problem. So the aviation industry is a very complex, very fiscally challenged. It's always struggling. They're trying to fit as many people as they possibly can in a plane. The margins are incredibly thin. Everybody, all of the big manufacturers are looking to aviation and looking to the aviary world to try and figure out anything they can do to get a leg up, or I guess a wing up, to use a bad pun. Owls have ridges on the largest wings in their feathers, so the largest feathers in their wings, excuse me. And that breaks down some of the turbulence as air travels across and over the wing. That actually cuts down a little bit of the noise, and it's being used right now by engine manufacturers to try and cut down the whooshing, the deep, low tonal whooshing sound, try and make passenger comfort a little bit better. So maybe they're squeezing a couple extra people in the flight, but they're going to say you don't need the noise-canceling headphones. Another good example is you can see the winglets at the end of the wings. That comes from hawks. All the way at the end of the wings, if you stick winglets out there, you prevent some of the downwash from flowing all the way down the wing, and you get more wind to fundamentally go from the front to the back of the airplane. That generates, 0.5%, 1/8% more lift. When it comes to fuel mileage, that's an enormous amount. That's another dozen packages FedEx can throw in a commercial aircraft. It's extra, all sorts of extra room. It's more water, more beer, more anything you can put inside of into an aircraft. Another example, our friend the skunk here. I think we all know that natural gas has a smell. Most people also probably know that natural gas doesn't actually smell. It's odorless. So, and a leak of an odorless hazardous chemical in a house, that's a really big deal. How do we try and use some known smell? How do we try and generate something that can effectively mitigate or effectively alert the broadest range of people in the world? Well, they use a chemical, I believe it's called mercaptan, and it's not from skunks, but it's based on the triggers that skunk smells actually initiate. So it's really modeled after our reaction of skunk smells. They're a little more polite, and it's not as painful or gut-wrenching, but the fundamentals and the way you feel it's all the same. So for Boston Engineering, what are some of our challenges, and how have we been able to execute based upon biomimicry? We were approached by the Navy. They have some very big vehicles out there in the waters that don't turn very well. And that's a bit of a challenge, especially in some simple cases when they're trying to maneuver in ports, or in tactically relevant cases, think of the hunt for Red October, of course. That's a humpback whale, our friend the humpback whale. You can see these funny little bumps on the leading edge of the fins. You can actually see in the background, you can see his other fin. You get a really nice picture of what those bumps actually look like. They're called tubercles. They create this complex phenomenon called cross-normal separation. I'll spare you guys the details. But what it does is it keeps the flow attached to the hydrofoil as it's moving through the water. These massive 60, 120, 150 foot whales can actually do this very, very, very tight circular motion as they try and corral fish. And that's why they jump out of the water. They're actually corralling fish in this circular motion, and then they're scooping right through the middle of it, jumping up and grabbing as many fish as possible. So what are we doing? We're actually applying that to some other underwater vehicles, trying to help some dynamic control, unsteady dynamic control problems to really try and maximize and ensure the amount of laminar flow. You can actually see on the right there, that's just a standard rudder. We can actually start seeing these on big fans. You start seeing these in a handful of other locations where high angles of attack and dynamic risk of flow separation occurs. Another maybe more well-known system for Boston engineering is the challenge of underwater vehicles. So in general, underwater vehicles are in kind of two different categories. The first one being ROVs, like you see here. Very good at inspection tasks. They can move around little by little, incredibly used by the oil and gas industry. And then there's another version called UUVs, and this is the hydroids and the remus, and it looks like, say, a submarine, but it's much smaller. And they can run very long ranges. They can do very standard missions, but they can't maneuver particularly well. So where might we come up with some inspiration? And I would venture to say that big old tuna is probably the best inspiration you could possibly find. These guys are incredibly fast. They're incredibly sleek. They're incredibly energy efficient. And they actually come naturally in sizes that might be pragmatic for operational, Navy, military, oil and gas missions. They come in a size that's actually pragmatic, so you don't have to worry about risks to scaling. So how do we do it? We try and reverse engineer it. We took real 80, 90 pound small tuna. We took it to a gentleman that was very patient and had a CMM machine. We were actually able to map the entirety of the structure, map the whole geometry. We were able to come out with a model that we were able to try and manipulate and suggest this is actually a real copy, a three-dimensional CAD model copy of what you actually see there. So these are some of the early models. Now we're moving a little bit more into the more modern area. We have a couple different skins that we can put on them based on what's important and what's required for the mission. Generally, what we're doing overall is we're really trying to help Customs and Border Protection try and identify risky items, whether they're attached to ships, whether they're contraband stored somewhere, whether there might be a mine somewhere, trying to help them work through their process a little bit faster. One of the key problems that they have is when they see something, they can stop the flow of commerce. But if you think some big port, say Port of Houston, if somebody stops a ship, they have 1,000 other ships waiting to try and get into that port. It is a giant problem. So they run this risk of not being entirely sure as to whether or not they really should stop a vehicle or whether or not they should let it go. All right, so what makes sense in the future? What do I think somebody were to tell me if I were in your guys' shoes? I think there are a couple key areas and key topics. The first one is interfacing, whether it's human-robot interfacing, which is something that I've been working on for quite some time, whether it's human-machine interfacing, but it's how to build that window in between an operator and a system. Let's start there. So it's really important when we think about human-robot interfacing or human-machine interfacing, you have to connect for people. We talk a lot about autonomy, we talk a lot about how that'll really change the world, but at some point decisions are going to be made, whether we think they need to be or whether the government decides that's a necessary check. Those decisions are going to be made by people. So it's really important to ensure that they can be made by people. So I showed you that first video of the DARPA Robotics Challenge. I think I mentioned I was very lucky to be able to go down to a couple of those big events and be a part of the team for DARPA. Part of the biggest benefits that I had when I was doing that work was I was actually able to go out and see a lot of the teams that were preparing for it. So I was able to really understand what went into their engineering. So this is a team called IHMC. They're down in Pensacola, Florida. That is a Boston Dynamics Atlas. It's a relatively well-known vehicle. I think most of you guys probably recognize it. But you can see that we have a 450-pound humanoid robot doing crane pose, standing, balancing dynamically on, there's actually a third cinder block sitting under there. So the capability of the engineering is unbelievable. It's absolutely incredible. I mean, this is literally the Kung Fu Kid, a giant robot Kung Fu Kid. But then, as you saw, when it came time to walk on slightly uneven cinder blocks, it had an enormously hard time. It was so difficult. It was painful to watch. So what is the actual difference? The difference between these two very similar scenarios are, the one on the left, the team that was driving and operating the robot was standing right behind the camera. They had all the data in front of them, and they had the actual vehicle right in front of them as well. So they had this unbelievable amount of awareness. On the team, when they were running on the right, part of the overall event was you had to take the robot, it had to do its events out in the field, and you were separated by maybe a quarter mile. You had to be 100% separate, and you could only interface through the eyes and ears and arms and legs of the robot. So when we did a boatload of research, we did an enormous amount of evaluations, we saw three general classes of people, or three general classes of teams that enabled this human-robot interfacing. So the most bottom level, people in the control rooms were interfacing with the robot. So they were using the interface that they were working through to make the robot do things. So it was kind of the lowest level. The middle level, they were using the robot to try and, they were using the interface to try and understand the environment. So they're trying to build their own mental model, their own mental map of what was going on in the environment. But the teams that did well and the teams that actually succeeded were the teams that were simply interacting with the environment. The teams that were actually turning those knobs and using the drills and opening the doors. The teams that weren't worrying about the window, that interface that brought the two systems together. Those are the ones that were the vastly far and superior. So that's a really important thing to focus on, that no matter what, no matter how advanced we can get the technology, there's always going to be that window between the human and the technology that could be limited. So we do an enormous amount of work for the Department of Defense and Homeland Security, as well as a lot of commercial ventures. And I come across photos and images like this, and this is like standard government. Nobody knows what's going on. Somebody's trying to make it look really intense and very professional and all this. So I think this photo is just, I think it's fantastic. But the important note, and what connects us to the slide beforehand, all of these lightning bolts, if you envision them as communication pathways, every single one of these communication pathways has to be incredibly efficient. It has to be able to enable somebody from one side to another to not just communicate, not just make that ship move, not just try and make that ship do something. They have to be able to do what the ship is trying to do. So as the web that we're building of user interfaces and robotics and systems, as that web gets bigger, the trust that's needed to ensure that when you're operating something, it's going to do what you want it to do, that trust web starts to get bigger and bigger and bigger. I think this is one of the really big problems as we talk about AI and we talk about moving forward in that technological space. It's one of the really big problems, because at the end of the day, there is going to be a human in there somewhere that will be in the loop at some point. And it's really critical to make sure that not just one, but all of those communication pathways are robust enough for thorough, deep-rooted trust so that operators can actually execute the mission, what they're actually trying to do. Something that I think in general, folks coming out of school have a big advantage of the people that are out is the design process. But imagine the process of trying to develop this car. It's a clay model. I can't even think of how long it took somebody. I mean, they were clay model people. That's what they did. That was their career. They built these and something was wrong. They had to try again, start over. It was this incredibly complex process. I've heard now that the most recent Corvette was built almost exclusively virtually from the human factors piece. What side, where's the steering wheel going to be? How's the gear shift going to go? What position is the operator going to actually be in? Where, all of those details to how is it going to be assembled? Everything, all of that was done virtually ahead of time. So you could change, modify the process, not just modify the hardware, but you could modify the process itself dynamically before you even built it. So when you think of the design process changing, that is unbelievable. So I encourage everybody, use the tools that you're getting exposed to. It's incredibly powerful. And the second you get into industry, you're going to find a lot of people that are not aware of what the newest technology and the newest design tools are. And it's, to be blunt, it's because they're lazy. They don't really want to have to relearn something. I remember learning SolidWorks and Pro-E and all this stuff, and you have to not be lazy. It's hard. So please keep that in mind. It's a really important point. So monitoring assessment is changing. It's another very, very important point and a big, big push. I'm sure you guys probably hear it in classes all the time. We talk about it in terms of Industry 4.0. Most other people call it in terms of IoT or IoT-related items. But there's a relatively basic roadmap. We first built stuff, and then we started building stuff in mass. And then we had other things build stuff, and now we have other things building stuff, and both of them are telling us how it's going. It's incredibly powerful. One really good example is not just the technological breakthroughs and the technological capabilities, but how you can marry really powerful business models to it. So Caterpillar, really big company, giant global, they make huge systems, they make some of the biggest tractors in the world. This is very easily considered old farm equipment. It's kind of the category they're in, industrial farm equipment. What they're doing now is they're doing a massive pivot to IoT, where when they ship out a model, they're shipping it out with the sensors. You don't even have the choice. They're shipping it out with the sensors, and that data is being provided both to Caterpillar and it's being provided both to the owners of the systems. So imagine two operators that are running, I think that's a road grader on the front there, two operators that are running the road grader. Maybe you have one that's a super user, and you have one that takes 2x more time. Right? That's data now that somebody doesn't have to rely in the field for, that somebody, the core operators, the owners can actually use and leverage. Maybe they say, well, we need to team those two up on a shift, right? Maybe we need to let, the lagger try and help pair him with the more advanced operator. So that's a very pragmatic technical piece. Now the bigger business model that Cat's interested in is they can now try and do preventative maintenance. And if you think these big systems, they're running really tight schedules, if Caterpillar can tell them your drive shaft's going to break in 6 weeks, your drive shaft might break in 6 weeks, first and foremost, the person that's operating it is going to say, get out here as fast as you can. I don't want to deal with it. I can't wait. I can't possibly risk the downtime when I don't know of it. So that helps the operators, and it helps Cat sell way more drive shafts. Every drive shaft they own, 6 months ahead of 6 weeks, 6 months ahead of time. That's an enormous amount of people going out, being able to bill at relatively high rates to change drive shafts and more drive shafts themselves. So it's a really important model to realize that the technology can really enable the business model and the business process. Back a little bit more to Boston Engineering. Now the newest version of Corvettes and some of the super tuners, we've been working with them to try and give them mobile in-car and back to the unit dashboards. So we're turning the entire vehicle in its own IoT sensor. So I can sit at my laptop at work and I can pull up data on a couple hundred Callaway Corvette drivers. I can see what they're doing. I can see how the system is working. And I can actually, well, I won't, but the Callaway folks can actually tell them and allow them to help tune it in situ. It's pretty unbelievable, right? And it's a really exciting thing. And it's technology that we're actively working on, and it's out there. I mean, it's a really powerful platform. So there's maybe another minute here, but that's all I have. I appreciate you guys being a great audience. If you have any questions, thank you.